the discovery of the spin-Seebeck effect that also stimulated to create this priority program. And within this program, we have a strong collaboration with Matthias Kloy, who perform measurements on different properties of the spin-Seebeck effect, as shown here, the thickness dependence, and also the suppression by using magnetic fields. And this result inspired us to study the length scale of magnonic spin currents, which are excited at different temperature gradients. And with that, I want to come to the outline. What we do is we use atomistic spin models, which I want to introduce as a first step, and then I want to present the results, what happened in ferromagnets, and in the second part of my talk, I want to extend these models to sublattice materials and discuss what happens in antiferromagnets and ferrimagnets. And what we do is we use a model with localized spins that sit in a cubic lattice, and we consider a Hamiltonian with exchange interaction, mainly limited to nearest neighbor interaction, anisotropy that provides an easy axis in z direction, and also we apply external magnetic fields. And as we heard in the morning, what you can do is you can calculate the Landau-Lifshitz-Gilbert equation, not for a macrospin model, but for each magnetic moment on the lattice. And this equation describes on the one side the precession of each magnetic moment around its effective field, which is given by this Hamiltonian. And also you have a relaxation that aligns the spin towards the effective field, and the characteristic parameter here is the phenomenological damping constant. And the temperature is included as white noise, which is added to the effective field, and it scales, for example, with damping in order to describe the strength of the coupling, but also with temperature. And with this dependence, we can define specially dependent temperature profiles and then study the excitation of spin currents within the systems. What we normally consider is illustrated here in these two figures. We have on the one hand side an extended heat bath at the hot and the cold end of the system, so we have a perfect sink and source and do not consider interface effects. And when we apply this temperature profiles, it remains constant in time, and the magnetic system then relaxes into quasi-stationary states in which we describe, for example, the magnetization. And we apply two kinds of temperature steps, or I present the results for two different temperature profiles. The one is the temperature step, and this we use to study the length scale of the magnonic spin currents, because you can think that you have like a source of spin current which is more or less locally, and then you can use on which scale you can see deviations of the magnetization. And in order to compare the simulations with experiments to the longitudinal spin-Seebeck effect, we use extended temperature gradients which are linear over a special length L, which you can vary. And the results I want to present in the following slide, at first for the ferromagnetic system. And if you apply such a temperature step, which is illustrated here, what happens is that you excite a net magnonic spin current. And what happens is that in the hotter area, you have more magnons than in the colder one. And so the magnons can propagate in each direction, but because of this difference in the density of states, you get a net current from the hotter towards the colder region. And this spin current will modify the magnetization of the system. So you see here in this graphic, very close to the temperature step, you see deviations of the local magnetization from the equilibrium value of the heat bath. And these deviations we call Magnon accumulation, just as the difference of the magnetization minus the equilibrium value. And you see in the hotter area, the magnetization is increased because you have less magnons than in equilibrium, whereas in the colder one, the situation is reversed. And the length scale of this depends also on the damping, because with lower damping, you get magnons that can propagate over longer distances, and so the magnonic spin currents will be larger. And you see that this magnon accumulation decays with length or with distance to the temperature step, and this we use to define a so-called magnon propagation length. And you see here the decay of the magnon accumulation in the colder area, where we apply T equals 0 for different damping constant. And what you see is that besides the regime at the beginning, the magnon accumulation decays exponentially, and then you can fit this and calculate the parameter of this exponential decay, which is then the magnon propagation length. The results are shown in this figure here. You see that the magnon propagation length as a function of damping constant and anisotropy, and the results from the simulation are included as data points here. And you see at the one side that it scales inversely with damping as expected, but you also see a strong anisotropy dependence. And to explain these results, we define an analytical model, and we use the linearized version of the LLG equation and solve it analytically, and then you can derive a dispersion relation, which is here, which has a frequency gap dependent on the anisotropy in this case, because we don't apply external magnetic fields. And then the second term describes the exchange coupling, and this cosine comes from the lattice structure, and for small wave vectors you get the Q-square dependence. Secondly, you can calculate the lifetime of the magnons due to the damping that you apply, and this lifetime scales inversely with alpha and with the frequency. And this model allows you then to calculate a frequency-dependent magnon propagation length by just using the decay in time and the group velocity that you need, or that the magnons, that the magnons propagate. And you can see here how this frequency-dependent propagation length look like. You see that for different anisotropies, you always get a defined maximum value, which you can calculate, and then you can find that the exponential decay of these magnons agrees with the maximum of the propagation length. So this temperature step gives you an estimate of about the maximum length scale that you can have. And you see here the lines are from the analytical values, and you have nice agreement. And if you would estimate the length scale, for example, for YIG, which is a soft magnetic material with low damping, you will find length scales of several micrometers, which are also in agreement with experiments. In order to compare our simulations with the spin-Seebeck effect, we apply temperature gradients with different lengths, and this can be then compared to the situation where you increase the thickness of the YIG. And we calculate again the magnon accumulation, so we calculate locally the magnetization profiles and the equilibrium values, and then extract the magnon accumulation out of it. And you find that in the hotter area of the system you have a lower number of magnons due to the spin current, and in the colder region the situation is reversed. The maximum appeared just at the edge of the gradient, where we were interested, because in experiments that is where typically the interface sets in, and then we observed the magnon accumulation just at the end of the cold end of the gradient, and vary the length, and what we find is a saturation effect dependent on the damping of the material. So what you find is that the saturation effect of this spin-Seebeck coefficient depends on like an averaged magnonic length scale. What you can see here on the next slide in the sketch here, what happens is that when you have a small film and you increase the length a bit, what happens is that the magnons from the hottest region now of the sample still can reach the cold end and contribute to this measured signal in the normal metal, or in our case in the magnon accumulation. But when you increase the thickness further, you overcome the average length scale of Magnon propagation. And now the hottest Magnons in the system, when they propagate towards the colder region, they're damped in average before they reach, and they do not contribute anymore to the measured currents in the normal metal, and that gives you a saturation effect that was found in experiments in the group of Matthias Kloy, and I think he will discuss the results in more details tomorrow in his talk. And what you can also do is you can apply external magnetic fields, and what you find in agreement between simulations and experiment is that you can freeze out or you can suppress the Magnon accumulation by a large degree using magnetic fields. In experiments here, for example, you see magnetic fields up to 9 Tesla, and you have a suppression effect of between 30 and 40%, which is quite a lot. If you now look at the frequency spectrum and the Magnon propagation length, you can see what happens, because what you do with an external magnetic field is you shift the frequency gap of the system towards higher frequencies, and you practically freeze out the Magnons below that regime. And this low frequency Magnons have the longest propagation length, and their relative contribution is higher than expected before, and therefore you have a strong suppression effect by the magnetic fields, because the energy you apply there are much smaller than kBt, so you would expect that this effect is smaller. And I want now come to the second part of my talk, where I want to discuss what happens in 2 sublattice magnets, and I want to start with antiferromagnetic systems. And in antiferromagnets, you now have 2 Magnon branches because you have 2 sublattices, and in the absence of a magnetic field, they're degenerated. But these modes, the single modes actually can carry spin dependent on the precession direction of the single sublattices, as we learned in the morning. And so the modes can carry opposite angular momentum. What happens to thermal spin currents? And as a second step, you can apply again magnetic fields, and you can split the Magnon branches. And then the probability with which these modes are excited are no longer equal. So we want to study in which cases, or if there are thermally excited magnonic spin currents. And what we do, again, first for the case with no magnetic field, we apply here a temperature step, and we look at the single sublattice magnetizations and calculate then in a similar procedure the Magnon accumulation out of it. And in the absence of magnetic field, what you find is that the sublattice Magnon accumulation, they really compensate each other at every position, so there is no spin current in those systems. Nevertheless, you see that you have a Magnon current, and you can calculate again the length scale of this current. And what we find now in this case is that the dependence is different to the ferromagnetic case, because the anisotropy dependence becomes much weaker, because the frequency gap depends differently on the anisotropy. And in total, you can estimate a propagation length that, in comparison to a ferromagnet with the same parameters, can be much smaller. And this is also because the lifetime of the magnons is different. If you now apply a magnetic field, as I mentioned before, you change, or the Magnon branches are no longer degenerated and they are splitted. So you could think that you excite a spin current because of the different probabilities to excite those modes. But what you see here is again the excitation around the temperature step here at z equals 0, and you see that you practically see no big difference. There is a spin current excited, but it is very small and practically negligible. Hmm?
What is the strength of magnetic field? Is that down?
I only have rescale units, but it is very close before spin flop. So, so it is a very, it is some Tesla must be dependent on the parameters, but I think it must be 1 to Tesla something. But it is like the largest fields we can apply before you have a spin flop transition. And you still don't see anything. The effect becomes even smaller when you have smaller fields. Yeah. And the last part is the spin-Seebeck effect in ferrimagnets. There were first theoretical predictions by Unuma et al. And they say, okay, the spin currents vanish in antiferromagnets, but they do not vanish in compensated ferrimagnets. And there were the measurements. We also heard in the talk from Garrett Bauer in gadolinium iron garnet, where they predict this here are the measurements from the group of Matthias Kloy that also contribute to that paper, where you can see a sign change at the compensation point and a second sign change at the smaller temperatures. And we wanted to study what happens at the compensation point. So we choose a toy model ferrimagnet with a 2 sublattice system. And we include next nearest neighbor interaction, and then we choose a parameter set that provides a compensation point. So we have a second sublattice that has a larger magnetic moment but a weaker coupling, and therefore it demagnetizes at much smaller temperatures. And therefore you have here in the system where the equilibrium properties are shown, you have clearly a compensation point at 0.7 in this unit system. And what we do now is we apply again a temperature step just to see in general what happens. And we vary the temperature level of this system in order to study the temperature dependence of the effect. And here in the above picture, you can see the situation at t equals 0 for the single sublattices. So you have a large contribution from the second sublattice because the second sublattice is very sensitive to temperature, and the first sublattice has only a very small change because there's stronger exchange coupling. So the total Magnon accumulation is determined by the change of the second sublattice system. If we now vary the temperature levels, you can see the results here. The Magnon accumulation increases with increasing temperature first. 0.7 was even the compensation point, so we see that there is no vanishing signal. What happens is that the signal decreases after at higher temperatures, and you see a sign change at around 1.7 in these units. And in order to explain this, we have a look again on the equilibrium properties. So you see the equilibrium magnetization changes first a lot, even has the largest changes around the compensation point, and it becomes flat at higher temperatures. And so we looked at the correlation between the Magnon accumulation and the change of the magnetization with respect to temperature, and we find that the temperature dependence shows very nice agreement. So to define the Magnon accumulation, we just use the difference at the temperature step, and then we calculated separately the derivative of the magnetization with respect to temperature numerically. And you see the plots are just put on together, but the scaling with temperature really is the same. So we can say that the Magnon accumulation in those systems is proportional to the change of the magnetization with respect to temperature. And this you can also see if you think of Magnon densities. You now have 2 branches, and you have to consider the gradient of the Magnon densities, but of the 2 branches, and add them up, and then you end up with this temperature scaling. And with this, I want to conclude my talk. I wanted to show you that you can define frequency-dependent Magnon propagation length, and you can use that in order to describe magnonic spin currents in different temperature profiles. And you can use this to explain some effects about the spin-Seebeck effect, like the saturation effect, which was shown in this paper by Kirberger et al., where we contribute with a numerical model. You can also use this to explain what happens if you apply high magnetic fields, and to explain the large suppression effect that was found on the spin-Seebeck effect, not only by us, but also by some other groups. And I wanted to show you that even in antiferromagnets, where you have no spin currents, you can still have heat current transport by magnons, which appear on a different length scale. And in ferrimagnets, where the situation becomes even more complex, you can find that at temperature steps, you have a scaling with a derivative of the magnetization with respect to temperature. And at the end, I want to thank DFG for funding. One side, of course, within the spin, within this priority program, but also within the SFB at the University of Constance. And you for your attention.